Next thing we're going to do that is related to probability. And this is something that you have life experience with, but you just probably don't know that you have life experience with it. It's what's called expected value. Okay, expected value has a lot of application in a wide range of areas. One of the main areas that you have impact with it is in insurance rates and things like that. All of that is based on expected value. So what is expected value? That's a great first question. So the expected value is the average result over the long term. Okay, just like anything else related with probability, it only makes sense to talk about something like expected value over the long term. So what this means is if I'm going into a situation, what amount, what value can I expect? That's why it's called expected value. What can my expectation of a result be over the long term? Okay, so we'll get to what that means. So here's how you calculate it. Okay, it's calculated by finding the product. What operation does product represent? Multiplication. Okay, it's calculated by finding the product for each outcome's probability and net result. Okay, so we're going to find the product of each outcome's probability and net result, and then we're going to add all those things together. Okay, it's not a super hard calculation. I wanted to just state it like that because our book, if you're reading along in the ebook or watching the videos in the ebook to supplement what we're talking about, then you'll see this formula given for expected value. You don't have to memorize this formula. You just need to know that you're going to take every outcome and you're going to multiply the probability times the net result. And so what that looks like as a formula is you're going to take the probability of the first event. So I'm going to put a little 1 there times the net amount or the net result of the first event. And then you're going to add to that. And you're going to do the probability of the second event times the net amount of the second event. And then because I don't know how many outcomes I have and whatever we're talking about here, what I'm going to do is I'm just going to put an ellipsis and then I'm going to go to the last one. And that last one, we're going to say the probability of the nth event times the amount of the nth event. So this is just the formula that represents what I said right above it. You're going to take each outcome's probability times the net result, and then you're going to add up all those products. Well, if that seems confusing, hopefully doing a couple of examples will make it seem a lot less intimidating. So here is my first example. One area, I don't know what your future holds for you, but if you get into any sort of business, then expected value plays a big part in things like this. Again, these are simplified examples just because we're just learning something, but the basis of these examples is in reality. So JetBlue is considering adding a new route from Boston to Minneapolis, and they've done some market research. So, you know, anytime you see a McDonald's or a Publix or anything else pop up somewhere, they have done extensive research about traffic patterns and customer habits and all that sort of stuff. Anytime a new big store pops up, that's all based on expected value. Somebody's done a whole lot of stuff like this, somebody who enjoys numbers. So after doing the market research, JetBlue estimates that if it adds the route, there is a 60% chance of making $800,000. There's a 10% chance of breaking even, and there's a 30% chance that they could lose $1 million. So what's the expected value? So they want to know, should they go into this? Is this going to be a net positive for them, or is it going to be a net negative for them? Because you know, if you're going to have a business, you want to make money. You don't go into business to lose money. So my expectation, my E, okay, E is just going to stand for expectation. Well, give me one of, there's 3 outcomes. Give me one of the outcomes. Okay, the make money. Yeah, the 60%. You don't have to do this. I'm not going to do this for any of the other problems, but just for your notes, I'm going to just write the words right up here, make money. Because I'm just telling you that that's the first outcome we're considering. You can do these 3 outcomes in any order you want. Okay, so I'm just responding to what was said. So this was already given, but I'm just going to ask again, what's the probability that they determine they're going to make money? 60%. So that is 0.60. Okay, we always use decimals Percents are just another way to write decimals. And what's the net result if we're making money? We're going to make how much money? $800,000. Okay, great. So what's the next event we got to consider? Okay, so the break even, sure. Again, it does not matter what order you do these three in. Okay, so that is not going to make you right or wrong on this problem. So break even. Well, what's the probability we break even? 10%, so 0.10. And then what's the net result? What does that mean to break even? Right, you make nothing, so it's 0. You break even. You didn't make money, you didn't lose money. Then the last thing that can happen is we could lose money. Or JetBlue could lose money, not me. What's the probability that JetBlue loses money on this route? 30%. 30% of the time, traffic habits are not going to support this route. And so then this case, how much are they going to lose? $1 million. And since they're losing it, we're going to make that negative $1 million. Once you get all the numbers in the right place, it just becomes a calculator problem at that point. So I am opening up my calculator app here. So 0.6 times the 800,000 is going to be 480,000. 0.1 times 0 is just 0. And then 0.3 times negative $1 million is negative 300,000. That negative is important. Okay, so don't leave that out. So then 480,000 plus negative 300,000, your calculator is going to tell you that that's 180,000. So whatever time frame JetBlue is looking at here, it's probably a year. I probably didn't put that detail into the problem. Whatever time frame they're looking at, every time they have this route for that amount of time, they can expect to gain $180,000. So for them, they would probably say, okay, that's worth our investment because we're going to make money by adding this route. If the expectation came out to be negative, then they would probably say no, okay, because we don't want to end up losing money. That's what expectation is telling you. So basically, in the long term, it's the number of times I run this route, I'm going to add up all the results and divide by that number of results, and the average is going to come out to be $180,000. You with me on what this is telling us? Okay, great. Well, let's practice some more. Exercise 1, giving you a super similar version of the problem, just so that you get to run through the numbers. All right, well, let's see how you did. And if you have any questions, any follow-up, let's get it out in the open. So the expectation, you're going to buy a stock and you're using an investment app and you find out that there's 70% chance in these market conditions that you're going to make 15,000. There's a 10% chance that you're just going to break even. 20% chance you're going to lose 8,500. So what's the expectation for you of this purchase? Okay, so I'm going to be an optimist for you. It doesn't matter what order you do these three products in though, okay? So that's not gonna affect your outcome. So being optimistic, we're gonna say 70% chance that we make money. So 0.70 times 15,000 plus, there's a 10% chance we break even, so 10% chance of 0, and then a 20% chance that we lose money, and we're losing 8,500, so that's a negative 8,500. Anybody get something different from one of these terms that we need to talk about? All right, well, help me out with the multiplication. What's 0.7 times 15,000? Thank you very much. 10,500 sounds good to me. And then plus 0, I'll write that in. And then plus, what's 0.2 times negative 8,500? Negative 1,700. Okay, sounds great. And when I take 10,500 plus a negative 1,700, that is going to be, is that 8,800? Yeah. $8,800. So your net is positive. Your expectation is positive. So in the long run, it would be worth making that investment. All right, so we're just going to go through different situations, again, simplified situations, but we're going to go through some other situations that you would use expected value. So for instance, if you ever get involved in event management, you want to know how many people you're going to plan for. Okay, so these in this particular situation, somebody's planning an outdoor event. And the organizers estimate that there could be 20,000 people if it's not raining, and 12,000 people if it is going to rain. So what we want to know is if there is a 30% chance of rain, what is the expected number of people that I can plan to have at this event? Okay, all right, so go ahead, you do this. Give it your best shot. Okay, there's two outcomes, either rain or no rain. So see how you do. All right, so my expectation. All right, so which outcome do you want to do first? Raining or no raining? Okay, raining. What's the probability it's going to rain on this day? Okay, so 0.30, 30%. And what's the net result if it rains that day? Okay, 12,000 people are going to show up. Great. Plus, so if the probability is 30% that it's going to rain, what's the probability that it's not going to rain? 70%. Yes, it's either going to rain or not rain. There's no other thing that could happen in those two options. And what's the net result if it does not rain? 20,000. Great. We're going to have a lot more people. So notice we're having a positive. There's positive either way. So 30% of 12,000, I think that looks like 3,600. 70% of 20,000, I think that's 14,000. And so a reasonable amount of people to plan for is going to be 17,600 people. Still doing okay? All right, we'll do the next, oh no, sorry, the next example is mine. The next situation we're going to look at as far as applying expected value is the idea of a lottery. Okay, so this example that I'm going to do, and then you're going to do one that's very similar. This is the simplest type of lottery you can possibly have. It's just one winner. Okay, there's one winning amount. But if you are fond of lotteries, if you like to play the Powerball or whatever, your expectation could be calculated in a similar manner, but it's a little more complicated because you could win with 6 numbers or 5 numbers or 4, and there's lots of different prize amounts. Okay, so that just becomes a little bit more of a complicated calculation. But this is the basis for it. So here we go. Josh attends a charity event and purchases a raffle ticket offering a $50 prize. The cost of the ticket is $2. If 100 tickets are sold, determine Josh's expected value for this ticket. And then there's a second question, what is the fair price? And we'll talk about what that means in just a minute. Okay, so we're Josh, and we're at this charity event, and we're gonna buy just one raffle ticket. So what are the two things that could happen to Josh here? He could win the $50 or he could not. That's why this is the simplest type of lottery. There's only two outcomes. Okay, win the $50 or not win the $50. Okay, let's be optimists for Josh. Okay, so he is going to win the lottery. What do you think the probability is that Josh wins this lottery? How many tickets does he have? Out of how many tickets? Okay, so in the bowl, there's 100 tickets, somebody's swirling their hand all around, and there's only one. So the probability that Josh wins this lottery is 1 chance out of 100. So that's the probability that he wins. Now here's another point to be careful on. What is the net amount that Josh goes home with? Right, we're familiar with the net amounts on our paycheck, right? You get your gross pay, that hopefully looks decent, and then what happens? Uncle Sam comes and takes some, and this person called FICA takes some, and then you end up with your net amount, right? What's left over. So think about this situation. Josh has gone up to the table. How much money is Josh given? $2. They call Josh's number, he gets 50. What's his net result? 48. There you go. Josh is $48 richer than when he started. Everybody understanding why that's 48? Okay, I'm just going to put a little asterisk here for your notes. This is the net result. I know we won 50. You're right about that, but he also paid $2 in. Okay, well, even though we were optimists, what's probably going to happen is Josh is going to go away disappointed. What's the probability Josh does not win this lottery? Yep, 99 out of 100. There's 99 other people with tickets, or there are 99 other tickets. What's the net result to Josh if his net number is not called? -2, yes. He loses that $2. Okay, again, once you get the numbers in the right place, that's hard to do. I totally understand. If you got a question or a comment, please ask it. But once you've done that, the rest of this is just some calculator work. 48 divided by 100, when you put that in your calculator, that's 0.48. And then when you put -2 times 99, and then you divide that by 100, so 2 times 99, and then I'm going to divide it by 100, that's -1.98. And so what that means is if Josh does this frequently, over the long term, every time Josh buys one of those lottery tickets, his expected result is to lose $1.50. Over the long term, if he's doing some financial planning, he's losing $1.50 every time he plays one of these little charity lotteries. Because most of the time he's going to lose, every once in a while he's going to win, and that's how come the average is going to work out to be that right there. You tracking with me? So the other thing on this problem asks for what's called the fair price of the ticket. We saw the word fair once before when we were dealing with probability. We were rolling a fair die or flipping a fair coin. That just meant that there was an equal chance of each side. It wasn't weighted. What the fair price means is how much should be charged so the expectation is 0. Okay, so the fair price means the expectation is 0. Remember, in math, the word fair does not have a moral connotation. That's a philosophy question. This is just saying, okay, we want to what would the charge be so the expectation is 0. And here's how you calculate it. It's a pretty simple calculation. I'm going to abbreviate. The fair price is equal to the expectation plus the cost. So when you're asked what the fair price of something is, then you're going to take that expectation that was -$1.50. You're going to add that to the cost to play, which was $2 in this case. And so if we were going to charge people just enough so that the expectation for everyone was 0, we're just doing this for fun, then that would be, you're going to charge everybody 50 cents per ticket. That makes the expectation work out to be 0. Doing okay? All right, we are almost done. We're on our last page. So flip page. Your next example is a problem just like this with different numbers so that you have to work through it. In exercise 3, there's 1,000 raffle tickets sold for $2 each. There's still just going to be one prize of $600. So what's the expected value if you buy one ticket? And then what's the fair price? What are the outcomes in this situation? What possible things can happen? Win or lose. Yep, there's only 2 things. That's why it's the simplest lottery possible. 2 things. You're either going to win the $600 or you're going to go away without winning the $600. So if we first do the outcome of winning, what's the probability that I win this lottery right here with my one ticket? 1 out of 1,000. Well said. Okay, you have one ticket out of the 1,000. So you have one chance out of 1,000 to win. What is your net result if you win this lottery? 598. Yep, you win 598. You paid $2 in. You went home with $600. So the net result is 598. The much more likely thing to happen is you're not going to win this lottery. So what is the what's the probability that that happens? Perfect. 999 out of the 1,000 are going to be non-winners. And so then the net result that time is -2. Okay, again, at this point, it becomes a calculator problem. So 598 divided by 1,000 turns out to be 0.598 plus -2 times 999 divided by 1,000 is 1.998 or negative 1.998. When I add those things together, that turns out to be -1.40. So that means that your expectation is you're going to lose a little bit less than the previous lottery. In the long term, you're losing $1.40 every time that you hand over your money to buy a ticket. The fair price of this one, the fair price is just the expectation plus the cost to play. So -$1.40. This one again costs $2. So if we were designing this just to be so the expectation turns out to be 0, then we should charge 60 cents per ticket. Any questions? Anything I need to follow up with? Just as an aside, if you like games of chance, if you are somebody who likes to go to the casino and push the buttons and stuff like that, every game of chance is weighted against you. Everything has a negative expectation. So like even a slot machine, most slot machines have an expectation of you're only losing a few cents every time. So your expectation is like negative a nickel or negative 2 cents. But the casino is counting on the law of large numbers, right? That you're going to do that a large number of times, and that's how they make lots and lots of money. Okay, so just I don't do much gambling because I know the math behind it more than anything else, but whatever you're comfortable with. All right, exercise 4. This one I'm going to step through with you because I've upped the ante in this lottery, so to speak. We're going to have multiple prizes on this, and we make a little assumption that's not quite right, but for our purposes right now, it'll be okay. So exercise 4, 10,000 raffle tickets are sold for $5 each. There's 4 prizes this time, okay? So that's how this problem is different than the last problem. We've got more outcomes. 4 prizes will be awarded. There's one $5,000 prize, there's one $2,500 prize, and there's $2,000 prizes. Here's the assumption we're going to make. Okay, this is not technically right, but you do not know how to do conditional probability yet. You will after spring break. That's exciting. Okay, but for now, we're going to assume that the probability of each ticket being selected is 1 out of 10,000. If one ticket is purchased, determine the expected value, and then we'll determine the fair price. So we're just going to go through this one at a time. The expected value. So here's what I want you to do. We're gonna first assume that we're winning the big prize, the $5,000 prize. So please write down what 2 things are you going to multiply together. What's the probability times the net result for the grand prize in this lottery? All right, what's the probability we win the grand prize? Perfect, 1 out of 10,000. Great. What's the net result if I win the grand prize? Excellent. Thank you very much. Well done. 4,995. We good so far? All right, do the same thing for the $2,500 prize. What's the probability times the net result? So what's the probability you win the $2,500 prize? 1 out of 10,000 again, yes. We said we were assuming that each ticket has that chance of winning. And then what's the net result in that case? Great job. Okay, here's the first thing that I want you to be careful on. I want you to remember when we do the outcome for the $1,000 prize, how many $1,000 prizes are there? 2. How many chances to win do you have? Okay, so do the product for the $1,000 prize. What's the probability I win the $1,000 prize? 2 out of 10,000. Yes, I've got 2 tickets. And then what's the net result if I win that? 995. Great. The last thing you got to be careful of is with the last term. How many prizes are there? So how many non-winners? Don't shout it out, but that's how you're going to calculate the probability. How many non-winners are there now? Okay, let's go with it. 4 winners. So that means there's 9,996 out of 10,000. That's the chance that you're not going to win. So the reason that's not 9,999 is because there's more prizes this time. Okay, so 9,996, and then your net result is -5 on that one. The rest of this just becomes a calculator problem. That's definitely the hard part to this, so just be careful. So 4,995 divided by 10,000 is 0.4995 when I do that division. And then 2,495 divided by 10,000 is 0.2495. And then I have 2 times 995 divided by 10,000. That is 0.199. Don't round yet. Don't round to the very end. And then we have -5 times 9,996 divided by 10,000. That's -4,4998. And when I go through and I do all my adding, we're just about done. We end up with -$4.05. That's your expectation in the long term on that lottery right there. Once again, the fair price, go ahead, I'm just going to give you 30 seconds. Do that calculation for the fair price. Fair price is the expectation, which is -$4.05 plus the cost to play. So if we were going to charge just enough so that everybody's expectation in the long term was 0, what we would charge for this is 95 cents. So we'd be giving people back a lot of nickels as a result of signing up for that lottery. All right, just 2 more applications of this. You're almost done. You're going to make it, I promise. Exercise 5. Again, this is a super simple example, but this is the expectation if you're the insurance company and you're signing up people to life insurance. You know, the whole point of insurance is you don't want the tragic thing to happen, but you are preparing for if it does. So for the insurance company, they've got to sign up a lot of people so they have enough money to be able to pay out when the tragic thing does happen. So of course, there's all sorts of negatives to that too, greed and government regulation, but that's not for us to talk about here. So exercise 5, I want you to figure out the insurance company's expected value. In this, I left off one bit of information because I'm not great at typing. So according to a life insurance mortality table, okay, insurance is all about what's called actuarial tables. They have probabilities for everything and everyone and all sorts of pre-existing conditions and all that. The probability that a 20-year-old woman will live for 1 year is 0.994. So we're being optimistic. We want this person to live. If a 20-year-old woman buys here's where I left something off, a $10,000 1-year life insurance policy for $100, what is the insurance company's expected value? So what this means is if the insurance company, every time they sign up a 20-year-old woman in this demographic and whatever, how much are they expecting to net as a result of that? Give it a try. I'll give you about 2 minutes to chew on this before we head to the last problem. So again, this is a super simplified example because you don't tend to buy things like life insurance for just 1 year. But things like your auto insurance, somewhere there is a computer with actuarial tables about your probability of getting in an accident based on your age and where you live and your gender and all sorts of other factors. And that's what determines your insurance rate. So in general, the older you get, the less you're going to pay for car insurance because your probability of getting in an accident tends to go down as you get older until a certain point where you get too old and it starts to go back up again, just because of the probabilities. So in this case with the life insurance, there's 2 outcomes for this woman. She's either going to live or die. Let's be an optimist. What's the probability this woman lives for the whole year? 0.994. It's almost a certainty. Okay, great. Remember, we are doing this from the vantage point of the insurance company. What is the net result to the insurance company if this woman lives for the year? You're the insurance company. She's paid you. So you what? You get $100, so that's going to be positive. From her vantage point, it's negative, right? Because she's paying. But we are from the perspective of the insurance company. Okay, what's the probability this woman does not make it through the end of the year? Perfect, thank you. 0.006. The only 2 things that could happen, she either lives, hopefully, or dies. Okay, those 2 things are going to add up to 1, so 0.006. Again, if you're the insurance company, what is the net result? She paid you $100. You're paying her beneficiary $10,000. So what's the net result there? Not minus 10,000 because you have that $100 sitting in your bank account. So it's minus $9,900 because you already got 100. Now you're paying out the 10,000. So when we pop that into the calculator, 0.994 times 100 is 99.4. And then 0.006 times negative 9,900 is going to be negative $59.40. And when I add that up, the expected value for the insurance company for every 20-year-old woman in that category, in that area of the country or whatever, nets them $40. All right, so exercise 6, I'm going to work this along with you just for time's sake. So exercise 6 says this. You're taking a multiple choice exam, because everybody's done that. And here are the constraints. There are 5 possible answers for each question. 2 points are going to be given for each correct answer. A half point is going to be taken away for a wrong answer. And there is no penalty for being blank. So the first question is, if I don't know the answer, is it to my advantage to guess? Okay, so it's an expected value problem. So expected value. Let's go ahead and assume let's be optimists. Let's say we're really good at guessing. What's the probability that I get the problem right when I guess on it? Yep, there's 1 correct answer out of the 5 possible options. And what is the net result to me if I guess right? How many points do I get? I get 2, so 2 points. Okay, so I'm going to put a 2 right here. Plus, well, if there's a 1 out of 5 chance I get the problem right, what's the probability I get the problem wrong? 4 out of 5, fantastic. And what's the net result to me if I get it wrong? Negative a half. I'm going to say negative 0.5. I'm losing half a point. So 2 times 1 divided by 5, that turns out to be 0.4, plus 4 times negative 0.5 divided by 5 is going to be negative 0.4. So the expectation is 0. So in this case, if I'm guessing a lot, it doesn't change any outcome. You might as well just not bother, okay? Because your expectation is 0. So then the follow-up question, the last thing we're going to do today is, okay, let's say I can eliminate one of the wrong choices. Let's say I know one is very, very wrong. is it to my advantage to guess? By the way, statistically, if you have a teacher that is not making tests well, the best guess is B. Okay, remember that, because most teachers use their best distractor on A, and then they put the right answer on B, and then they put their weaker distractors, unless somebody has taken a good statistics of testing class, which I have. So if I give you a multiple choice test, don't guess B, guess something else. Okay, so here we go. The expectation is this: if I can eliminate one of the distractors, I know it's wrong. Well, what happens to my probability of getting the problem right? It becomes what? 1 out of 4. And you get 2 points. And then what's the probability that I get the problem wrong? It becomes 3 out of 4. And you lose half points. And just for time's sake, I'm sorry I've gone a minute long here. I'm just going to tell you, once you do the calculator work, this is going to turn out to be positive 0.125. And so what that means is that since it's a positive result, it is to your advantage to guess, because over the long term, you're going to be adding to your score.